Okay, second crash course is on matrices. Remember the movie The Matrix? You know, you had all these data points in all these rows of data and then all these columns of data. Well, that's all a matrix is. It's just a rectangular arrangement of numbers in rows and columns. They just made it look way cooler in the movie, but that's all it was. It was just a bunch of information that they knew how to read and that a computer knows how to read. And that's why we use it today so often, is because it's a very easy way for us to pass a lot of information to a computer. Because a computer isn't as flexible as us. It can't take a point as like 1, 2, like we know that that's the x and y coordinate. The computer needs that x and y coordinate broken up into those two separate pieces of information, and then it can do whatever you tell it to do with it, but you got to give it each piece of information separately. So let's dive in. Each number in this matrix is called an element. So notice that the element in the second row and third column is that 2 that they highlighted right there. And the dimensions of a matrix are just the numbers of rows and columns. So this has 3 rows, 4 columns, so we could call this a 3 by 4 matrix. And what we're going to do with it is use it to represent points and figures on a coordinate plane. And so the way we're going to do that is by using a 2-row matrix where the first row gives us our x coordinates and the second row gives us our y coordinates. So again, really quickly, matrices are so important because computer science is so important to us. And the reason they're so important is because it's a really convenient way for us to pass information to a computer. The rows and columns are just easy to take in a ton of data. And math, like any other language, has to evolve to meet our needs, and our needs these days are really heavily computer science related. And so we had to figure out math that's going to work for computers, and that's where matrices or matrices come into play. Okay, so write a matrix to represent the point or polygon. So it's really simple. Again, we're just going to use 2 rows. The one row is going to represent our x, the next row is going to represent our y, and so for point A, that's just going to be this matrix. Notice these square brackets that we use, and -4, right? If we have A, the x value is -4, and the y value is 0, and so you get a -4, 0 matrix. That's it. That's point A. That's how you'd represent point A with the matrix. For quadrilateral ABCD, just notice we're going to need 4 points. We still have 2 rows, but now we're going to need 4 columns because A is going to be represented with this column, B, C, and D, and you can pick out any of those points. C, for instance, is 1, 2, 3, 4, up 1, so that is 0.41, and notice right there, C is 4, 1. So we're representing a point or a bunch of points in a polygon as a 2-row matrix where each point gets an x and a y coordinate in 2 rows. So the next thing we need to be able to do is add or subtract matrices, and to do that all you do is add or subtract the corresponding elements of the 2. So in the first one you can see we have this 2 by 2 matrix and we're adding it to another 2 by 2 matrix, and so I'm just going to add the 5 and the 1 and you get 6. I'm going to add the -3 and the 2 and you get -1, and so on and so forth. I'm just going to go around and you end up with your resulting matrix is 2 rows, 2 columns. You have 6, -1, 9, -10, and the same thing is down here. So in this case we have a 2 by 3 matrix that we're subtracting from another 2 by 3 matrix. So we have 6 minus 1. We have 8 minus -7. So notice that's going to end up being positive. We have 5 minus 0. So 5 minus 0. And we just go through each one, each corresponding element, and we end up with 5, 15, 5, 0, 11, -4, and we again have a 2 by 3 matrix. For our last example, we're going to add 2 matrices together to perform a translation, sort of like we did with the vectors. And it sounds a little more confusing than it is. It's pretty simple. So let's just go through this. First, we have this triangle ABC. I'm just going to connect it right here. And so I'm just going to write the points, right? This is 1, 1, 5, 0, 3, -1. So notice that how they wrote it over here as a matrix. A is 1, 1, B is 5, 0, and C is 3, -1. And so that is how we show that triangle as a matrix. right? And that's how you would show it. That's how you would give that information to a computer, because the computer knows, okay, that first row is going to give me all the x coordinates, and the second row is going to give me all the y coordinates, and it can piece that together and put it onto the grid for you. And that's why we use it. But now it says find the image matrix. So where is this going to end up if we use the translation 1 unit left and 3 units up? So what we're going to do is we're going to add our triangle ABC, which is 1, 1, 5, 0, 3, -1. And notice we're going to change each of those points, A, B, and C, by the same change, which is 1 unit left, which means the x is going to be -1. We're changing that by -1. And 3 units up, which means the y coordinate, we would be going up 3 or +3. And again, we're going to do that for each point. So for A, B, and C, we're going to be making the same change. And so when we add those together, remember how we do the matrix addition. It's just 1 plus -1, which is 0. 1 plus 3 is 4. 5 plus -1 is 4. 0 plus 3 is 3. 3 plus -1 is 2. And -1 plus 3 is 2. And so this would be our A prime, B prime, and C prime. And we can map that. So A prime ends up being 0, 4. A prime. B prime is 4, 3. So 1, 2, 3, right there's B prime. And C prime is 2, 2. So 2, 2. And C prime. Now let's connect this triangle. And just notice, just like with the vectors, each of our points moved the same amount. Each of them moved 1 to the left and up 3. 1 to the left and up 3. 1 to the left and up 3. And so that's how you would show translation using matrices. You'd be adding what we call the translation matrix, which is just telling us what movements are we making, right? This is called our translation matrix. And up with what we call our image matrix, right? This was our original polygon undergoing this translation, and you end up with that image of it.